I hope you are all having a great day. I am Mr. Ish. Thank you for joining me. In this video, we're doing slightly something different. A topic of perhaps shyness for many students, learning the cosecant x and the secant x graphs. A very essential topic nevertheless. We will do a step-by-step procedure. You will learn how the cosecant x and the secant x graph develops. But we will do it indirectly. We will do it by means of the sine and the cosine. The best way, in my opinion, is to look at everything in terms of their original functions. Then you do the reciprocal to get to the cosecant and secant x. Start with the sine x graph. We're not looking at tangent or cotangent yet, but in this video we're focusing on that. Draw a 1 and a -1. A very important point about the sine is it's an odd function and it goes to the origin. Therefore, you have a key point over here. You want to remember all of these x-intercepts because sine of these values is always 0. One is a pi, the other one is a 2 pi. You have a minus pi, and then you have a minus 2 pi. The intermediate values in between these would be your pi over 2, 90, 270, minus 90, minus 270. Sine is always an x-intercept at these dotted areas. 2 pi, pi, 0 pi, minus pi, and minus 2 pi. Sine of 90 is always a 1. Sine of minus 90 is a -1. Sine of 270 is a -1. And sine of minus 270 is a +1. Connect the dots. And this is what you have, your basic sine curve. Now, when you go from the sine to the cosecant, you know what you're doing. You're basically doing a 1 over sine x. So wherever you had an x-intercept is an area where you would have a potential 1 over 0, which is undefined, and you know you can't do 1 divided by 0. At any of these areas where you have these x-intercepts, pi, 2 pi, minus 2 pi, it would be undefined because you'd have a 1 over 0, and for the cosecant graph, you end up getting a vertical asymptote, because when you do 1 over 0, you represent that in terms of this as a vertical asymptote. Minus 2 pi, minus pi, 0 pi, 2 pi are your vertical asymptotes. Now, in each of these areas, you make your mental breaks. You have a upside down u, a normal u, a normal u, and an upside down u. Wherever you have these, you do their flips exactly from the point 1 or -1 upwards. So your cosecant graph would look something like this. In this area, this little upside down u became a normal u. In this area, this normal u became an upside down u, and you're seeing that develop. Here, a normal facing u became an upside down u. And remember, these curves are going to go along these vertical asymptotes. Here you have an upside down u, or you can call it n, but you're going to do a projection upwards. Now that right there is your cosecant graph. What you can do now, if you want, erase the sine. There's nothing wrong with doing that, and what remains will be your cosecant graph. That right there is it. You have the asymptotes. Now, the next hard part, and we will do the same for secant, is the range and the domain. Which one is easier? The range is easier. The range is down to up. Look at it. Each of these instances, you have something coming here from minus infinity all the way up to this -1, and then it stops over there, but that value -1 is very well included. You have from minus infinity coming up to -1, but it's included. Then you have a little jump. You jump from here to here up to 1, but the 1 value is included, hence you have these square brackets here, and then it projects up towards positive infinity. If you want to be a little bit more imaginative, you could imagine what would have come over here. You would have had a projection over here, and here you'd have a projection coming from here like this, but you don't have to add this extra projection. Right here, what we have is perfect. Now for the domain. The domain is not minus infinity to infinity. It would have been were it not for these vertical asymptotes, but it isn't. Your domain will be, you can see it in multiple ways. How about this? X is an element of all real numbers, except x cannot be the following values. What are these values? Where you have these vertical asymptotes. So you can say wherever x generated a vertical asymptote, you cannot have that x value in the domain of cosecant x, and these are 0, pi, 2 pi, minus 2 pi. You can always write it in this way. You can do 0 plus or minus pi n, because these asymptotes are showing up after every 180 degrees, either on the right or on the left. That can be a good way of representing your domain. Absolutely nothing wrong with that. So this right here is your domain. X is an element of all real numbers, except x could not have been any of these areas where your vertical asymptotes popped up. Secant, we'll start here with the cosine. Where are your values? I always like to just do pi and 2 pi. You can do minus pi, minus 2 pi. You can even go by 90 degrees if you want. We'll just identify those as these unidentified marks are my 90 degree angles. Here I'm a little bit off in my spacing and it will look bad, so let me fix this for you, otherwise it will look like a distorted cosine and a secant curve. We have a pi, minus pi over here, then we have a minus 2 pi. Here's my minus pi, minus 2 pi, minus 270 and minus 90. We know cosine is a even function and cosine of 0 is always a 1. But cosine of all of these 180 degree multiple angles is always 1 or a minus 1. Cosine has x-intercepts, or it's 0 at all of the 90 degree multiples. 90, 270, minus 90, minus 270. At cosine of pi it's a minus 1. At cosine of a 2 pi is a positive 1. And you can start connecting it. You have something which looks like this, and it's coming here and it's going right over here. Now you've done this, you have to determine the secant is the reciprocal of 1 over cosine. So wherever cosine was a 0, you'll have a, in terms of its reciprocal, an undefined 1 over 0. And where was it 0? At these 90 degree. So you will have these vertical asymptotes develop at 90, 270, minus 90, minus 270. So that's the area where you cannot have a value in terms of the secant, because you'll have this come up. Now it's exactly the same. Wherever you have a down facing u, in terms of the secant, it'll be an upward facing. Here I have a downward facing, I'll make it upwards, and it's going to graze along these vertical asymptotes. Here I have an upward, so I'm going to do it downwards. Here I have an upward half, I'll do a half upward. Here I have an upward facing u, I'll do a downward, and that's my secant right there. And from this I can just do this, and there it is, the secant function. But now if you want, you can erase this, and what will remain will be your secant function, and then we can look at the domain and the range. The range of secant is exactly the same as the range of cosecant, because again you're looking from down to up. It's easy. The range is exactly this, from minus infinity it's coming and it's stopping at minus 1, including minus 1, because these values are very well included. Then it jumps right here to 1, and that 1 value is included, then it goes up to infinity. Now for the domain, you can do again here. X is an element of all real numbers, except x cannot be these values where you have a vertical asymptote. What are these? Pi over 2 multiples, but pi over 2 plus or minus pi n. Why am I doing pi over 2 plus or minus pi n? Because from this, it's not 0 we're starting here from 90, but the next one is 270, which is 180 degrees away. We're 180 degrees here in this direction, but from this 90 to minus 90, we're here on minus 180 degrees, which is a pi. So we're going in multiples of pi n, starting from pi over 2, and there it is. And that's about all I wanted to show you. Thank you for watching. Have a nice day.